So what we did until now, we have found y as a function of time, okay? And now we replaced into x function of t, because in x function, in dx by dt, we have y. This is why we started by finding y function of time. Then we replaced into the equation of dx by dt. Okay, so now what we obtained is dx by dt is a constant. So if we integrate this equation, we can get the expression of x, and x will be equal to, so by integrating, we get x equals to minus u0 times sine constant c1 times omega over v0. This is constant, and the whole term is constant with respect to time, times t plus c2 plus c2. Okay, so until now we have y function of time and x function of time. Okay, our purpose now is to find the path line for that pass through the origin at t equals 0. So first, in order to find the path line, the strategy is to eliminate, you can eliminate time between the two equations. Okay, so if you want to find any path line at any for any position, okay, the first step, you can eliminate the time between the two. But here, because they already gave you at time t equals 0, x equals 0, y equals 0, you can also, if you want, you replace t by 0 into the two equations, okay? And you can get from x equals 0 and y equals 0 what are c1 and c2, okay? So first, let us find the general path line, and after we will replace, okay? So if you say that for t equals 0, y equal 0, okay, what will be c1 if you replace into this equation? So you know the condition. You want the path line that for t equal 0, we have y equals 0 and x equals to 0. So from the first equation, y equal v0t plus c1, you can deduce that c1 is 0, because if you replace t by 0 and y by 0, you get c1 equals to 0, okay? And the same, if you consider your second equation, x as a function of time, you have that for t equals 0 also, we have that it's passing by the origin, okay? So y equals to 0 and x equals to 0. So if I replace here, I get that c2 is also 0. So now what are the two equations for me for x? For x, I have 0, okay, because I have that c1, my c1 is equal to 0. And for y, it's equal to v0 times t. Now, once I got my my two constants, okay, I can get my streamline, my path line, sorry, because if I eliminate t between the two relations, I can get that x equals 0 and c equal to v0t. Okay, if you want here, no need to eliminate time. Why? Because x is independent of time. Okay, because if you go back to your relation, you have that if you eliminate time between x and y, you can replace t by what if you want to eliminate t between the two? From your first equation, you can say that here, okay, you got your two relations, x function of t and y function of t. Okay, if you replace in x function of time, if you replace c2 by its value, okay, you have that c2 is 0 and c1 is also 0. So replacing c1 by 0 in this relation, you get that x is equal to 0 plus 0, so it's 0. And c2 is equal to 0. If you replace in the equation of y here, y is v0t plus c1. So if we replace c1 by 0, we get that y is equal to v0t, because c1 is equal to 0. So what we deduce here is that x is equal to 0 and y is equal to v0t. So no need to eliminate time between the two, because already x is 0. Okay, so your line is simply what is the y-axis. Because if I want to represent this path line, okay, this is my frame x and y. This is x and this is y. If I want to represent the line x equals 0 and y equal v0t, it will be the vertical line. So no need to do any elimination of time between the two, since x is already not function of time. Okay, now we will see another example where we can eliminate time.
How did we say at the end no x equal 0?
Yes, so at the end we deduced that the path line for which passes by the origin at t equals 0. So if you take a particle, what is the mean of the path line? If you take a particle that was at the origin at t equals 0 and you follow it, the path line of it will be, the equation of the line will be x equals 0. This is the meaning of the path line. The path line will take a particle and will follow it. That's it. Okay, when they gave you the condition and the particle passed at t equals 0 by x and y equals to 0, these conditions will help you to find the constants c1 and c2. So these conditions at t equals 0, x equals 0 will give you c2, and the condition at y equals 0, t equals 0 will give you c1. Replacing the constant by their values, you can get that x is 0 and y is equal to v0 times t. So if you want to draw the path line here, okay, it will be along this line, along x equals 0. So it's the y-axis. Okay, now we will see that another path line for t for the particle which was at the origin at t equal pi over 2 omega. This means here that I am following a particle that passed by the origin when t was equal to pi over 2 omega. So if I want to find what is the equation of its path, I should repeat the same methodology, but using different boundary conditions. Okay, so the only difference here is the same method we will use, but when we find c1 and c2, we will find them using a new boundary. Okay, because we already have developed the equation of y and the equation of x. So we have that, for example, for y, the equation is v0t plus c1. And for x, the equation is minus u0 sine c1 omega over v0t plus c2. To find c1 and c2, first, to find c1, I will start by which equation? By the equation of y. Okay? To find c1, they told me in the second case that it passed by the origin for t equal pi over 2 omega. So what I will do here to find c1 for the second case, the particle passed by y equals to 0 at t equals to pi over 2 omega. So now what I will do, I will just replace. Okay, so if I apply the boundary condition for this equation, I get 0 is equal to v0 times pi over 2 omega plus c1. Okay, so I deduce, so c1 is equal to what? So c1 is equal to minus v0 pi over 2 omega. Okay, and now I have found the value of my c1. The second step, I need to find c2. To find c2, I do the same. I apply the condition on x. Okay, so the second condition, that x is equal to 0 also for t equals to pi over 2 omega. So if I replace in the equation of x, so replace in x equation, okay, what do I get? I have that x is equal to minus u0 times sine of C1. What is C1? I can replace C1 by its value. Okay, I will replace C1 by minus V0 pi over 2 omega. So minus V0 pi, okay, over 2 omega. This is the value of C1. Then I multiply C1 as in the equation of x by omega over V0. So times omega over V0. What do I get? V0 will be simplified, okay? And also omega will be simplified. So I get sine of minus pi over 2, okay? So, and I should add now plus C2. And okay, don't forget also to multiply by t, okay? So your result here is multiplied by t, which is pi over 2 omega, okay? Plus C2 equals to 0. Plus C2 equals to 0, okay? So now, if you look at your equation, you can replace, as we said here, omega and V0 will be simplified. So you get that x is equal to, or 0, because we are applying at the corresponding time. 0 is equal to sine of minus pi over 2 is what? It's minus 1. And you already have a minus outside, okay? So you get a minus is plus. So U0 times pi over 2 omega times pi over 2 omega, okay? Plus C2 equals to 0. So now you can deduce the value of C2. So C2 is equal to minus U0 times pi over 2 omega. Okay, and now once you have your constants C1 and C2, you can replace back and you get x function of t and y function of t. And if you want to find the Pathline equation, all you have to do, you can eliminate t between the two equations, okay? Which is very simple. You can get t from one equation and replace in the other. For example, if I consider here, I have that x is equal to u0 times t, okay, plus a minus, sorry, because here if you do the expansion, minus u0 times omega times pi over 2 omega, okay? So now, if you want to find what is t function of x, what you can do is you will take this term to the other side. So you get that t is equal to x plus u0 times pi over 2 omega, okay, divided by u0, okay, which is equivalent to, it's equal to x over u0, so it's x over u0 plus pi over 2 omega, plus pi over 2 omega, okay? Once you get t function of x, you can replace into y, okay? So replace into y, you get y function of x. You get y as a function of x, and this is your path line, okay? This will define the path line, which is the trajectory of the particle if you follow it, okay? Now, of course, each particle will depend on the boundary condition. So if you take a particle that passed by the origin at t equals 0, the path line will be different than the path line of a particle that passed by the origin at t equal 1. And this is what you can see here, because when you replaced back, if you replace t by its function of x, you will get your path line is y equal v0 over u0 times x. Okay, so by just eliminating here, if you want also, you have a simpler technique, because look, if you look at your expressions, the term t minus omega over 2 pi, you have it in both equations. So here, an easier way to eliminate t is to say that this this number t minus pi over 2 omega, you can replace it by x over u0 or by y over v0. So here, because it's simple, no need to do the substitution. You can directly say that if I eliminate time, I will get that x over u0 is equal to y over v0. Okay, and this is the equation of your path line. So the path line equation, is equal to y equals to v0 over u0 times x, and it is a linear, it's a linear shape. Okay, so if you follow the particles that passed by the origin at t equal to pi over 2 omega, you will observe that it's going over a straight line. Now, to do small analysis, let us see graphs. Okay, we will see graphical representations to understand more what is happening. Okay, so look, what we did together, first we have found streamlines. In the first part, in part A, we have found streamlines at two different times. One that passed by the origin, so this is your origin. Okay, since you have unsteady application, then if you take, as we said, if you take a picture of your flow field at t equals 0, it will be different than the picture of your flow field at t equal pi over 2 omega. So if you take a picture at t equals 0 and you want to track the streamline passing by the origin, you will observe this. You will observe this line, this one. Okay? While if you consider another time, if you take the picture at t equal pi over 2 omega, and you are looking at the streamline passing by O, you'll observe this line. So this is the streamlines. Okay? Now, for the path line, you have a particle, let's say it's emitted, it's injected in the flow field at t equals 0 at the origin. If you follow it, we have seen that it's along the y-axis. So if you follow it, you will have this line. On the other hand, if you follow the particles that passed by the origin at t equal pi over 2 omega, you will get this line. Okay? And we can demonstrate that for this type of flow, if I take particles, if I follow particles at different times, all will move along straight lines. Okay? Because you can come up with a general path line equation, a function of a certain constant, and this constant will depend on the time, if you want, the particle passed by the origin. So these are path lines for particles passing by the origin at different times. Okay, so if you follow particles passing by the origin at different times, you will get straight lines. Okay, but not the same lines. They will be varying with time. Now, from here we can define a new line which is called streak line. What is the idea of a streak line? The idea of the streak line is, if I inject several particles, so let me clear and the drawing. If you decide to inject several particles in the flow field, so imagine that you have a flow field and you inject several particles in it. It's like, if you want, when you put a tracer gas in a flow. Okay, when you put a tracer gas in a flow, you inject several particles at different times and you follow them in your flow field. So imagine that, for example, the first particle was injected at the origin at t equals 0. Okay, and after this you injected another particle at a different time, etc. Okay, so the particles that you injected at t equals 0 will follow what? Will follow the line on y-axis. So if you want to track it, let's say, for example, you decided at t equal 10 seconds, for example. If you decided at t equal 10 seconds to see what is the position of your particles. This one will be the farthest one. It will reach the highest position. So the first particle, let's say, will be here in this position. The second particle will be in the path of the next time, okay? Because you have the particle injected at t0 will follow this path, while the particle injected at another time will follow another path. So now, at a certain time, if you are looking where your particles are, okay? Let's say you want to see what your particles are at t equal 10 seconds. What do? You already found the equation of the path line. So you replace in the first equation t by 10, you will get that it is at this position. And you find an equation for the path line of the second particle and you replace t by 10, you will find that it is in another position. You will do the same for all particles you are interested in. So at the end, your particles will be at different positions, okay? Because they are injected at the origin at different times. And if you join the particles, their location, you will obtain what is called the streak line, okay? So if you want the streak line, mathematically, we don't have a technique if you want to just calculate it. It's a little bit complex because the idea is that you will take one position from each path line, okay? And if you take the position of particles from different path lines and you join the positions, you will get what is called the streak line. And the main application of streak lines is in experimental cases. So you inject a tracer gas or you inject particles in a flow and you can see them. And when you see them, you can track their behavior with your flow. And of course, if it's a steady flow, your particles will have you will have same streamlines, same path lines, and same streak lines. So for steady flow, if you want, your particles will follow the streamlines and path lines. But for unsteady flow, your particles will go over the streak line, okay, which will join several points of the different path line at a certain time t, okay. And of course, for unsteady state, at each time t, you have a different set of streamlines, different set of path lines, and of course, different streak. Any question on this problem? Okay. Now we will do a problem on another idea, which is acceleration along a streamline. Okay. So if you want, these are only the two main ideas of this chapter: how to find streamlines, path line, and streak line, and how to calculate the acceleration or if you want, any gradient. Okay. So for example, here we have an incompressible inviscid fluid flow that is steadily passing over a sphere of radius r, and the velocity field is given. So we know the velocity field. It's given by v0 times 1 plus r cube over x cube along I. So they already told you that v is only along I, no component along y, no component along k. Okay, so it's, if you want here, it's like a one-dimensional flow. So I have velocity in one direction. Okay, now what we want to find is to calculate the expression of the acceleration. Okay, so I will go back to the definition. What is the acceleration? The acceleration, okay, yes, okay, as you like. You are telling me that you have an exam at 5. Okay, I will stop here because you have an exam. We can do this problem next time. Okay?
Thank you, Doctor.
Thank you so much, Doctor.
Bye-bye.
Bye-bye.